welcome to your weekly AI update. We're tracking major developments in neural networks and the latest in advanced robotics.
A significant advancement in tracking neural networks and robotics is the creation of a Unified Neuromorphic Robotics Platform, UNRP. Key concept: the UNRP integrates real-time neural network activity monitoring with robotic kinematic and dynamic feedback into a single, comprehensive visualization and analysis environment. It's designed to provide a neuro-robotic twin that allows researchers and engineers to observe the internal workings of AI directly alongside the external physical actions of a robot. Key features: Neural Activity Mapping (NAM). Real-time visualization displays the activation patterns, synaptic weights, and information flow within a neural network as it processes sensory data and generates motor commands. This could be represented as a dynamic 3D graph where nodes, neurons, light up and edges, synapses, thicken or change color based on activity. Layer-specific deep dives. Users can zoom into specific layers or even individual neurons to examine their precise input-output relationships and activation functions. Thought bubbles. For interpretation. For higher-level networks, e.g., those using attention mechanisms, the system could generate textual or visual thought bubbles, explaining what the network is attending to or recognizing at a given moment, e.g., identifying object cup, detecting edge table. Robotic kinematic and dynamic overlay, RKDO. Synchronized digital twin. A high-fidelity digital twin of the physical robot operates in perfect temporal synchronization with the real robot. This twin displays joint angles, end effector positions, velocities, accelerations, and forces in real time. Force/torque visualization visualizes stress points or excessive forces on robot joints or grippers using heat maps or colored vectors. Trajectory prediction and deviation shows the intended path versus the actual path taken by the robot's end effector, highlighting any deviations. Cross-modal correlation engine, CMC. Causality mapping. This is the most innovative part. The CMC actively maps specific neural network activations or patterns to corresponding robotic behaviors. For example, if a certain cluster of neurons fires, the system can highlight the precise robot movement that results from it. Error source identification. When a robot makes an error, e.g., drops an object, the CMC can backtrack through the synchronized data to pinpoint the exact neural network state or sensory input misinterpretation that led to the fault. What if? Scenarios. Allows users to modify neural network parameters, e.g., adjust a weight, introduce noise, in a simulated environment and immediately see the predicted impact on robot behavior, without risking the physical robot. Benefits. Unprecedented interpretability. Provides deep insights into why a robot behaves the way it does, moving beyond black box AI. Accelerated debugging. Drastically reduces the time and effort required to diagnose and fix issues in AI-driven robotic systems. Enhanced training. Offers real-time feedback during robot training, allowing for more targeted adjustments to neural network architectures and learning algorithms. Improved safety. By predicting potential failures based on neural activity, UNRP can preemptively prevent dangerous robotic actions. Foundation for Explainable AI (XAI) in robotics serves as a critical tool for developing and validating truly explainable AI models for complex robotic tasks. The UNRP would be a game-changer, transforming how we understand, develop, and trust autonomous robotic systems. Advanced implementation and future directions, adaptive feedback loop and self-correction, AFLSC proactive anomaly detection. The UNRP wouldn't just display data, it would actively analyze patterns. Using machine learning on its own vast datasets of neuro-robotic twins. Performance. It could identify subtle deviations in neural activity or robot kinematics that indicate an impending failure before it occurs. For instance, a neural firing pattern slightly different from successful past attempts might trigger an alert. Automated remediation suggestions. Upon detecting an anomaly or error, the AFLSC component could suggest specific adjustments to the neural network, e.g., increase learning rate for layer 3 during object recognition, fine-tune weights connecting visual cortex to gripper control. In highly autonomous versions, it could even implement these minor adjustments in a simulated environment for validation, and with human oversight, apply them to the live system. Reinforcement learning integration. The platform could serve as a rich environment for reinforcement learning agents. By providing immediate, granular feedback on both neural states and robotic outcomes, the RL agent could learn more efficiently, understanding not just what actions lead to rewards, but which internal states of its neural network are most effective. Multi-robot and swarm integration, MRSI. Network of neuro-robotic twins. For scenarios involving multiple robots or swarms, the UNRP scales to provide a simultaneous overview of all agents. It would display the individual neural states and physical actions of each robot, along with their inter-robot communication patterns. Emergent behavior analysis. This allows researchers to track how individual neural decisions contribute to complex, emergent swarm behaviors. If a swarm fails to achieve a goal, the system could identify which individual robot's neural states or communication breakdowns were the root cause. Distributed AI debugging. Debugging distributed AI in multi-robot systems is notoriously difficult. MRSI would provide a centralized hub to visualize the decentralized intelligence, pinpointing issues in coordination algorithms or individual agent decision-making. Human-robot collaboration, HRC module. Predictive human intent. For collaborative robots, cobots, the UNRP could integrate sensors, e.g., eye tracking, gesture recognition, to predict human intent. It would then display how the robot's neural network is interpreting and adapting to the human's anticipated next action. Transparency of robot decision-making. When a cobot performs an action, the HRC module can quickly explain the neural reasons behind it in an easily understandable format to its human counterpart, fostering trust and improving collaboration efficiency. Shared understanding visualization visually represents the robot's understanding of shared tasks and goals, highlighting areas of agreement or potential misunderstanding between human and machine. Technological underpinnings. High bandwidth neuromorphic interfacing requires ultra-low latency data streams directly from the neuromorphic hardware or GPU-accelerated neural network simulators. Advanced data fusion algorithms, sophisticated algorithms to synchronize and correlate diverse data types. Neural spikes, activation values, joint angles, force readings, sensor data, LiDAR, camera, IMU, interactive 3D. Visualization engines, utilizes game engine technologies, e.g., Unity, Unreal Engine, or specialized scientific visualization toolkits for rendering complex neural structures and robot kinematics in real time. Edge computing and cloud integration. For large-scale deployments, edge computing would handle immediate, low-latency processing, while cloud resources would manage long-term data storage, complex simulations, and cross-robot learning. The UNRP, through these expanded capabilities, moves beyond just a diagnostic tool to become a complete development, deployment, and operational platform for the next generation of intelligent, autonomous, and collaborative robotic systems. Engage with UNRP to accelerate your research, refine robotic behaviors, and educate the next generation of AI engineers. Explore this transformative technology today.